Hello and welcome to the BE1-FLEX video series. Today we're talking about the self-testing analog inputs. For decades, protective relays have had the ability to monitor their digital core in real time with something called self-diagnostics. What's been missing is the analog components such as analog inputs as well as physical outputs that have physical transitions. With the BE1-FLEX, we can utilize the extra slot capabilities due to the high density of the inputs and outputs and utilize those board positions and board slots for this self-diagnostic capability. The analog to digital conversion of the Flex is board level, so by the time it gets to the motherboard, it's actually digitized and it provides 100% analog duplication if you're utilizing a second board. To set up the device, I'm going to go into BESTlogicPlus and go into my style configuration. So a normal application might call for only a single board, but we're going to call for two boards of either the same type or redundant capabilities to bring it in. Those redundant analog inputs, either current or voltage, are going to be looking at the same CTs or PTs that the original and primary one is. So to set this up, I'm going to create two circuits. One's going to be primary, looking at the normal voltage and current that protective relay would. I'm going to be looking at this particular slot and validating which physical inputs. Next, I'm going to create a second circuit. I'm going to call this my backup circuit. And this backup circuit, again, is going to be looking at the same power system components, looking at the same CTs and PTs. It could look at different CTs and PTs if you wish. But for this example, we're going to assume that it's looking at the same one. But I'm going to be bringing it into the device via a second slot on the device. And again, the analog to digital conversion puts all of the analog components purely redundant by having that second board capabilities. So once I've created the two circuits, I'm going to go down into my protection, which is where I'm going to monitor the difference between those in real time. So with our configurable protection, we can look at most any metered parameter in the device. So in a normal circumstance, if everything is healthy and everything's reading properly, I should expect to see zero difference between these two measured signals. So one method to do it, I'm just going to do a simple subtraction. I'm going to look at my circuit 1, and I'm going to be looking at positive sequence current, and that way I will get in the magnitude and angles. And I'm going to just compare it to that circuit 2. So under normal circumstance, again, I'm looking at the same thing. I should expect a zero difference, but if there is a difference, that tells me that one or the other analog card has a hardware issue. So now I set my threshold to something that is unexpected. The threshold is basically to accommodate for things like measurement errors and things of that nature, accuracy errors. So once I've got the configurable elements set up, all I have to do is go into my logic and figure out how I want to enunciate this particular condition. And this one in particular, I'm going to drive an indicator. I'm also going to drive a physical output. So same with any logic, drag it around, 100% visually graphical. And if that configurable element trips, I'm going to toggle an indicator as well as a physical output. Finally, I'm going to go down into my advanced settings and look at my targets. Whether you want a target for this condition or not is debatable, so you can enable or disable those targets as desired. So once I've created that settings file, I didn't go through the full settings configuration because it's likely that the device is used for other things, but ultimately I'm going to upload that settings file to the device. Once I've done so, now I'm going to jump over to my simulation. So here you see the BE1-FLEX. Imagine it has two boards looking at the same CTs and PTs on the back. On the right, you see the HMI, either remote or local, with a graphical representation of that phasor diagram of the primary circuit. So if I go to my real-time data, I'm looking at voltage and current of my primary circuit, and I see a standard 120 degrees separated phase current. If I look at my backup, you're going to see that it's exactly the same thing. Again, because I'm looking at the exact same CTs and PTs, I would expect them to be 100% equal, or 100% minus the expected accuracies. So for my simulation, what I'm going to do is I'm going to do a ramp test, and I'm going to start ramping the backup circuit. So let's say hypothetically it starts to lose calibration, which doesn't really happen with digital products. More likely than not, if anything were to happen, a fuse would open or something would occur where it would drop out. But for this example, we wanted to show the sensitivity of it. We show the backup starting to ramp down, and if I jump to my configurable protection, I can even see that difference calculation moving in real time. So as it increases in difference between those two circuits. Once it hits 0.1, I'm going to see that alarm pop up on the top. That would also populate the indicator on the front, as well as that physical output, and the operator or system operator can go out and know that they have a hardware issue to address. So again, if I look at my primary, I see it all as 5 amps, and I look at that phase A current of my backup circuit, it has actually been dropping, and it created an issue in a discrepancy between the two. So that's the ability to test your analogs in real time with the BE1-FLEX. Thank you.